Okay, we continue a little bit theory, then we go for revision. Okay, before this morning, we stop at this example 3, where we calculate the space that we can fit in the alien atoms, or we do it alloying. So we have show you how to calculate, and then what is the coordinate number, right? And there is a equation to calculate the critical radius, R star. All right. Okay, now we go into the defect. We go into defect or crystalline imperfection or defect. So there are few defect. There are few defect. I give you all. So there are few family. One is point defect. Okay, point defect. Which is 0 dimension. Then 1 dimension is line defect. I'll show you the diagram later. Then 2-dimensional defect and all this lah. So you go one by one. Okay, point defect. Point defect is actually we call it hole, but in engineering material we call it vacancy. Don't use hole. Don't use hole in your answer. Use vacancy to represent that there is a missing atoms or missing sphere at that space, at that plane or that space. So the first is called point defect, where we given a name called vacancy, means something missing in that position, right? Or one atom is missing. Okay. So when there is a hole missing, your atom, when talk about metals, it's like you are arranging a snooker ball. When there is a missing snooker ball, you can push, right? You can push the row, and they will fill up the gap. So when there is a vacancy, means it's more easier to deform. It's more easier to deform or reshape. Means the structure become weak lah. Become weak lah. Okay. So the keyword here in engineering material is called atomic mobility. So it gives atomic mobility, they're able to move, to fill in the vacancies. Okay. All right. Now in metals, they are rarely happen for vacancies. It's about 1 in 10,000 atoms. Very rarely in metals. Then to form one vacancy, your energy is 1 eV, 1 electron volt to take one atom out. Okay. Okay. So how does the hole or vacancies appear more and more? It's through these 3 mechanisms. One, plastic deformation. What I mean by plastic deformation? You pull the metal, pull until it reach plastic region. So again, when we look back the tensile graph, you have an elastic region, right? Elastic region. What I mean by elastic? You pull, you let go, you go to original shape. It means if you pull here, you let go until this point. Even there's a hole there, it will go back. You pull, right? It will have hole, it will have vacancy. But when it stay within the elastic region, you let go, it will go back to original shape. Means it will fill back. It will fill back the vacancy. So after elastic, then there's a plastic region here. Plastic means you pull and then you stay at the last pull length. So you pull, then you stay there. So this is when plastic deformation happen. There's a whole position at that particular location. Okay. Then more and more vacancy, it will contribute to the fracture point lah. Fracture point. Okay. Or rapid cooling from higher temperature to lowest one and trap the vacancies. What does it mean? You warm up the metal, You warm up the temperature. You warm up, then it becomes soft already. It becomes soft, then they're going to start to move already. It's like you melt a candle lah. You melt a candle, it like start to bend. Then when it start to bend, you rapid cooling. You bring down the temperature down, means you freeze it. So when you bring down the temperature, less energy, less vibration, then you will trap the vacancies. Embalmment of energetic particles such as neutron, this is on radiation, means this is a metal, let's say, and there's a radiation, you shoot a radiation atoms to hit this one. Means you shoot from a radiating source lah. Radiating source. Then you shoot this one like a bullet hole. This one will, you give energy to this one will bounce out. So here become one vacancy here. Okay. So either by pooling plastic or rapid cooling from high temperature, it trap the space there, or you bombard with the neutron. You bombard with neutron. Okay. So this process is important for migration or diffusion atoms in the solid state. It's important. These vacancies, they will help the migration of atoms in solid state. Means if there's a vacancy there, what does it help? It helps to migrate. Means this one can slide. It's like you're pushing the table snooker ball. When there's a vacancy, you can push. When you can push, means deformation. You allow deformation. Okay. Then there's one equation for this one. Also very popular equation. This one. Almost every test or final exam will ask you this one. With this N sub V is a vacancy formula. Vacancy means hole. Vacancy. NV equal to N exponential means E. E power something. Exponential minus QV KT. This formula won't be given in the test or final exam. So N is a number of atomic site. QV is the energy, will be given. T again in Kelvin. T is in Kelvin. K is Boltzmann constant. This one sometime will be given, sometime won't be given. 1.3 10 power 23 joule per atom K, but normally will be given lah. So when this one given, you know that there are two value. There are two value. If the question give you joule over atom Kelvin, you use this one. If the question give you EV over atoms Kelvin, you use this one. It depends on what parameter you have. If the question give you EV, then you use this one. If you are given joule, then you use this one. EV, you use this one, 8.62. So don't use the wrong value lah. It depends on the Q value here. It depends on Q value. So if your Q value given in joule, then you use this one. If the Q value use EV, then you use this one. Means this value. Okay, it depends on Q lah. Okay. And R is 8.31. This is also constant. This one. EXP is E. There's a small E in your calculator, right? The orange color one. You press that one, then remember to use the exponential. It's a power something. Then remember to use the bracket also lah. E, then exponential, then bracket it. Okay. So the step for this one, you calculate the Q divided by KT first. Then remember it's a negative sign. So it's an exponential negative value. Okay, there's a tutorial question for that. So let's say you are given, the question asks you to calculate equivalent number of vacancies per cubic meter in copper. So it asks you, in 1 cubic meter of copper, how many vacancy inside? At 1000 degrees C. Again, when you see this kind of question, remember, don't use Celsius, use Kelvin. Use Kelvin. Energy vacancy. You see, this one give you EV, so use the EV K value. This energy for vacancy is Q. So your K value, use the EV one, 8 point something, use that one. Atomic weight density is given. So atomic weight, 63.5 mole, and volume is density is given. K value in this case is not given, right? But you know lah. So if there are two lah, there are two. Just in case lah. But yeah. But before the assessment, remember to ask me. Remember to ask me whether this one given or not. Remember to ask me, because I will forget whether I put in the question or not. If not given, then got mark one. If it's given, then it's something else. So the marks will go somewhere else. Okay, so you know that you need to use this one because it asks you to calculate the number of vacancies. So NV equal to N exponential minus QV divided by KT. So the first is to calculate the Avogadro number. How to find the N? N is Na rho divided by A. Okay, so this one, N is the total number of atomic site. So means at that mole, you got how many atomic site? So you take, basically is in that volume, you calculate by dividing the volume. Okay, so this one is in gram per mole. This one is gram per mole. So you want to Avogadro is atom per mole. So you can take away the mole. Then you multiply by the density. So you actually getting the how many atoms per meter cube? Anyway, this one. This one is actually is conversion. 1 cm equal to how many meter cube? Because here you need to be careful on the unit. Here you are using cm cube, but for unit SI calculation, you see the question asks you what? Cubic meter. So you need to convert your answer in cubic meter. Meter cube. Okay, so that's why you see 10 power 6 cm cube over meter cube. This is actually a conversion of all the units. Okay, so you do this substitution, you find the N, then substitute back. QV you have already. All right, QV you have. So QV is from the question 0.9. K, remember why we use 8 and not the 1 point something? It's because the Q is given by EV. You need to match the unit so that you can cancel out. Then remember the temperature change to Kelvin. Why? Because your Boltzmann constant is in Kelvin, so that you can cancel the unit also. Okay. Then you'll find the number of vacancies is how many holes per meter cube. So inside here got how many holes per meter cube of copper. Okay, careless mistakes is the temperature. Some of you might forget to change to Kelvin, and then you might remember the wrong Boltzmann constant, or even is given, you might choose the wrong one. Okay, so the rest is the substitution. Okay, we have done with the point defect. Okay, point defect. Yeah. Okay, we have done with the vacancy. We are done with the vacancy. Now we go into point defect. What mean by point defect? Point defect is interstitial defect. Okay. Means you force one of the atom inside the space there. Okay, it's called point defect. There are two types of point defect. One is self-interstitial, means there's additional member in that space because of the maybe orientation, right? So so it's like you super cool the thing, is not enough time to go back to original, so it's stuck there. So you have a self-interstitial defect, or you have a vacancy defect. Just now, the equation that I write on the whiteboard there, NV, that one to calculate this one, not this one. Okay, this one to calculate the vacancy. So very clear on the diagram. On this slide, very clear. One is whole, one is with the additional things, right? So sometimes the question just give you a free marks by using sketch the vacancy and self-interstitial, or use a diagram to represent a vacancy and self-interstitial defect. Just draw like that. So you draw very simple one, a few circle, but you miss one circle in the middle, or you draw a complete one and then you add one more in the center. Yeah, correct. But this one normally is the same size from the host lah. It's the same size. Okay. All right. For ionic crystal, they meant to do this one. So for ionic crystal, they need patient and anion, positive charge, negative charge, this vacancy. So this, when they involve charges, ion, there's a name for it. It's called Schottky imperfection, something like this. So they have two. One is Schottky imperfection with its hole, and another one is Frankel imperfection. Frankel means, you see what is happening. Frankel means you got additional body there lah. But Schottky means that there's a hole there. Okay, but this one is due to imbalance of positive negative charge. Okay. Okay. So there are two. One is Schottky, one is Frankel. Frankel. Okay. This one, presence of this defect, either Schottky or Frankel, because they are involved with ion, then they will increase the conductivity. It's something a bit new. If you involve Schottky or Frankel, they will link to conductivity because they are ion. Okay. Another one is substitutional impurity. Yeah, this one is substitutional interstitial type. They can also because of impurity items. Okay, another one is called line dislocation. Let me see. Okay, line dislocation. Just now is a point, right? Point means one dot like that. Point means how you form a line. You form by dot, right? So you have one row of point defect, it become line already lah. Okay, so line, it textbook is called lattice distortion centered around a line. Means the hole is along the line. Right. So they are created by all this region, reason, solidification, plastic deformation also, vacancy, condensation, and atomic mismatch in the solid. So there are two types of line defect, edge and screw types. So I'll show you these two on the line category. Okay, I'll show you all the diagram. Okay, so this is H. What I mean by H? You see there's a missing line here, missing line of atoms here. Means this one is a normal one, then this one normal, but missing one line here. So how you mark line defect? This one is called H defects because it stopped at here, then no more. Then you draw a inverted T here. It's like no more way to go. So it's like inverted T here. Okay. So it can be upright, it can be inverted. This one is inverted. Okay, this one also same. This one also same. Right here, no more line to continue. So they have a H dislocation here with the inverted T. Okay, sometimes bonus question also, we will draw one box like that, ask you to mark where there is the H dislocation with the inverted T. Means we will remove this one. Actually ask you to draw this inverted T on the figures. Okay. Under microscope, you will see. Means this one you'll see like why suddenly there is a missing line there. You'll see that there is a stream of line like squeezing the things. Okay. Then in the another one is called burger or slip vector B, like this one. Slip vector is perpendicular to the this. So it means that you can use your left hand rules. Like if this one is the one that is coming out, then is this direction. So let me show you another one. Okay. Okay, before that, if you view in the 3-dimensional, so since this one is missing, right? This one is missing. So when you have a force acting around the object, this one will try to go down, right? This one will try to go down. So it will have a compressed effect here. Then this one will try to pull the things. Okay, this one might not be very clear. I'll show you another one. Show you another one. Okay, this one. This one, you know that when you observe, you know that this one got missing line of atoms. So there's an inverted T here. The action stop here. So action stop here. When there's a force from this side, you press this side, right? So this one don't have anything. It still continue to push. But when the force push this side, there's more room for it over here that you allow this one to push further. So there's more pressing here, right? More pressing here. And this is the vector. Vector means how many steps that this missing part can move. Like for example, this atom can move like how many vector they can move, right? This vector. Okay, so something like this. So this is another type is called screw dislocation. This one's like shear force. It's like earthquake. One move up, one move down. It's like move like this. Then this one will move in the screw. The burger vector will move in the screw behavior. Okay, so screw one is a 3-dimensional. Right, it's a 3-dimensional. This one you use right hand rules. This one go up, then your finger follow the arrow. Right hand rules. Okay. So the H is the 2-dimensional one. You see this one? This one is two-dimensional. It will go with this one. It go with this one on a plane. Burger, is it burger, is it? Okay. Burger vector is where does the atom can move? For example, here missing, right? So where does the atom can move? This direction, right? So this one cannot move, right? But there's a space here. So how does the atom can move this direction? Or this direction also can. Means in this direction. But the screw one, the it's like tectonic plate like that. You like move up and down. But this one is the cutting plane. Then this one move in the anti-clockwise direction. It's like screw dislocation line. Okay. So this one is more on shear stress by a cutting plane. Then you'll form screw dislocation. Okay. So this one is more on the shear plane. It's like how you tear your paper. Okay. You will cut like that. Okay. This one is another presentation online. So this is when you see there's a tectonic movement like that. This one is a screw. You know this one is a screw dislocation. And the vector is going this way. Right? It's going parallel to the plane. The cutting plane, parallel to cutting plane. So this one is from the top. You view from the top. Okay. Okay. Now important is you know how to draw the Burger vector. Burger vector for screw, it follow the plane. Yeah, you start from the top part, then you draw an arrow, go to meet the another plate. That is Burger vector. Okay. Okay, then there's also have a mix between edge and screw. So for example, this one. So here got missing edge, right? So missing edge, but this one, the burger is moving this way, moving in this direction. So the edge from B to A, from come out from here, it can also form a screw. It means one side got edge, one side got screw. On the object itself, on the crystal itself, you got two dislocation. It's a mix. Okay. Edge is edge. This one is edge. This one is screw. But it happened on the same metal plate. Means then you have two. It become mixed. Okay, so you'll see something like this. Line distortion. This one under SEM. You need to zoom in at 50 multiplication on the alloy. When you see all this like a crack, then this is a dislocation. Okay, we see point defect, we see line defect. Another one is called plane defect. Plane defect is very obvious. You can see with the naked eyes. So there are few. There are few. External surface is what you can see. External surface. Okay, this one you read lah. This one you read. Grain boundaries is like what I explained, the roti, the bread that you make. So if you grow crystal from embryo to critical radius, then go to the crystal. When crystal grow, it become boundaries. Okay. So this is the planar defect. So you will see okay. So grain boundaries is this one. This one is the grain. This one also like grain boundaries. This is a planar defect. Okay, planar defect. Boundaries. Okay, this one you read lah. Okay, another one is called twin defect. Twin defect is a mirror image. It's a mirror image of structure exists through the plane. So this one you look under microscope, and after you do etching, you'll see different color on the things. For example, you'll see this straight line like a runway, parallel runway like that. So this one is called twin, like two line like that, go parallel. All right. So how this behavior, you see this like a pink color like that. How this happen? How this happen? I'll give you a diagram. So this one is recrystallization happen. So when we learn phase diagram later, we will revisit the concept of recrystallization. Means you grow the crystal. You grow the crystal. So it will schematic diagram. It look like this. There is a shear plane here. There's a shear plane between the left hand side and right hand side. Then they form a twin plane. Then this one is a misalignment. This one can visually, this one planar defect, you can look under microscope. So for example, this one high grain boundaries, you can see that there is a space here along the grain. Then this one also got a grain over here. Got space. So you can draw a line there. Okay. Okay. So when you see this T, you know, right? This is the line defect. So mean the reach here, then no more already. Reach here, then no more already. Reach here, then no more already. This one for your info only lah. I won't ask you this low boundaries things, right? But from this, you know lah, the inverted T is a line defect. Okay, missing here, and missing here. Okay. So another one is called twist. So twist boundaries is like a misalignment between the two grain. It'll be like this. It will twisted like that. Stacking fault. This one you read lah. Stacking fault is like, what I mean by stacking fault? When you arrange the balls, okay, you arrange the ball. So the most obvious one is let me see. Let me find a more clearer picture. Okay. Stacking mismatch means let's say the first layer is this light blue color, second layer, third layer. So sometimes they do not follow the sequence. like A, B, then change to C, 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 A, something like that. That's called mismatch of stacking. Okay. So stacking fault means you're not following the layer by layer. There's a mixing of layer, like A become B, B, A, B, B, C, D, something like that. You do not follow like a sequence like A, B, C, A, B, C, A, B, C, A, B, C, but there's a repeat of another layer. Okay. Volume defect, this one is very direct. We call it void or pole. You can see with the naked eye one very deep hole like that. This is three-dimensional defect or volume defect. Okay, so this graph will tell you by examination under microscope, you know that you can categorize them between either grains defect or atomic defect. This one is all this. And these are the instruments that you can use to detect the range. Okay, detect the range. Okay, this one you read lah. This one you read. This is the steps where you cover in your lab, like step one, you do what until etching. You need to polish all these things. Okay. Another microscope, that one is under qualitative information about the material. This is microscope. This microscope, how microscope works. Lights come in, they reflect, then bounce back to the earpiece, right? Okay, so this tell you that a well-polished surface and got defect, what is the difference? Okay, so this is the perfect case where when you can reflect light, you see very flat surface. But when you see there is a line there, or you see there is a black color on the microscope, then it means that you are seeing boundaries. When you add etching agent, you see all the boundaries come out. Where does this black color? Because there is a loss of refraction. It do not bounce back to the microscope, but it reflect away. That's why you see dark color on the microscope. Okay. So all this you read lah. Okay. So it explained to you why you see all these black colors under microscope, because of reflected lights. Okay. Okay. This one, grain size. Grain size, to determine the grain size, is 2 power n minus 1. There is a grain size for you to determine. There is a standard there. Okay, so average grain diameter you can given by D equal to C divided by NLM. What is C? C is a constant. So 1.5 is typical microstructure. NL is a ratio, number of grain. M is a magnification. So let's look at this example. So ASTM standard you use to determine the grain size with the magnification of 100. What ASTM grain size number of the metal if there are 64 grain per square inch? So you use this formula, n equal to 2n minus 1. So n given in the question, 64 grain per inch equal to 2n minus 1. Then you, because you want to eliminate the exponential, base number 2. So what you do, you use log. log left side, log right hand side, you can pull the n minus 1 to the front. Then you can find your calculator, rearrange, you get n equal to 7. Okay. So if they are 60 gram per square under 200, okay, then there is a calculation there lah. There's a calculation there. Okay. But I won't ask you this one. I won't ask you. Just for info, there's a way to calculate grain size. Okay. SEM we don't have, but it was used for to do all these things. So this is a SEM machine. It's very expensive machine. You can see the sample up to this magnification, 180 in the microstructure. Okay, looks something like this. We don't have this one in our INTI yet. We hope we can get, but the utilization rate is very low, right? Okay. Then TEM is another machine you use for material science. TEM. So a few names of equipment for material research. One is microscope. Another one is SEM. The third one is TEM. At least you know lah. At least you know what instrument you can use. So the differences between SEM, TEM is the image that you can see lah. How clear they can see under certain microscope. So TEM you can see atomic already. You can see atom already. This one high definition TEM, more expensive and more detailed until you can see atomic size like that. Okay. Some more advanced one like this one, normally in the NASA lab, you'll see there's a tip of this 70 micron. Right. And so on. So these are the image that you can get. This one you read lah. This one for your info. Okay. So we watch this. Okay, this video you go home.
The scanning electron microscope.
Very long video.
Scanning electron microscopy is one of the most fascinating examination methods. This video shows how it works in practice.
For your lab.
Main components of the microscope are column for electron beam generation, specimen chamber, vacuum pump, monitor.
Okay, these are the sample questions that might be come out for chapter 4, right? So these are the things that might come out. Okay. All right. So with this, we conclude chapter 4.